So anyone would like to tell what we did in the last class? I know it's a week time ago, but anyone would like to recollect? We saw about training data, test set, validation set, and we also saw about cross validation, where we will use the test set and so on. Specifically, we saw K-fold cross validation. So these are the things we did in the last class. In this class, we will see about overfitting and underfitting. If time permits, we will also see about neurons. So what we will see in overfitting and underfitting is that sometimes our system would have not learned enough. Sometimes it would have learned very much. How to strike a balance between this is what we will learn in this class.
Ma'am, are you using your notepad or are you sharing?
Oh, I'm sharing. Sorry, 1 second. Is my screen visible?
Yes, ma'am.
Okay. So what we are going to do in today's class is that we are going to learn about overfitting and underfitting. In that, what we will learn is that we want to determine whether if our system has learned enough or it has not learned enough. We want to strike the balance between these two extremes. So we will learn how to strike the balance between learning too much and not learning too much. So what is the purpose of machine learning system? It is machine learning system helps us to extract meaning from the data. So in order to learn, we need to learn from the finite set of examples. From the finite set of examples, so we have a set of examples. We will learn from it. What we will learn? The general set of rules, which is applicable, which is inherent in the examples. We will learn the general set of rules to extract meaning from the data. Once we have learned this general set of rules, we can go and deploy it in the real world. So once these rules are learned, then we can apply these rules to the new data so that we can extract some information. Whether it is a person or a computer, learning a general set of rules from a subject or a finite set of examples is a tough challenge. Why it is a tough challenge means, first thing, when we don't pay enough attention, what will happen is that our rules will be very general. Then it can lead to wrong conclusions. On the other hand, if you pay too much attention, our rules will be very specific. Then again, it can lead to wrong conclusions. So not giving enough attention, learning general rules is called as underfitting. Paying too much attention and learning specific rules is called as overfitting. So among underfitting and overfitting, the most common problem and the most troublesome problem is overfitting. There are some techniques to control overfitting. It is called as regularization. So when we don't pay enough attention, our rules are very general, then the machine learning systems can lead to wrong conclusions. This process is called as underfitting. When we pay too much attention, when the machine learning model pays too much attention to learn, it learns very specific rules. Then also when we learn specific rules, we'll see how learning specific rules can lead to wrong conclusions. So this process is called as overfitting. The most troublesome of the two is overfitting. Overfitting can be controlled by a technique called as regularization. So what is overfitting? Overfitting is when our model learns too well and it does not generalize with the new data. Underfitting is when our model does not learn well, doesn't learn well. And both of them performs poorly in the new data. This is the definition of underfitting and overfitting. Let us take some one general example. Imagine you are going for a function which is very much crowded. You do not know a lot of people there, but you start exchanging introductions, you exchange small talks with others, and you interact with others. Suddenly, a person comes. His name is Walter. He has a big mustache. Then you make a mental picture. A person having a big mustache is called as Walter. And you meet another lady. She is wearing a beautiful turquoise earring. You make a mental picture that someone who is wearing beautiful turquoise earring is called as Erin. What happened that evening? You meet another person with a big mustache. Immediately, you recognize that person to be as Walter, but that person is a different person. His name is Bob. So, so what is that? Is that here you are trying to, our mental picture is misleading us. Someone is having a big mustache, you immediately name that person to be as Walter. Someone is wearing a beautiful earring, you immediately name them, you make the mental connections and you call them as Erin. But that is not the case here. It is not like we didn't learn the names correctly. We have learned the names correctly, but we didn't, what we is that we didn't learn them in a way that it didn't generalize when we meet new people. So we try to make an association with someone's appearance with their name. So there is a strong connection between these two ideas. So the connection between like having a big mustache is called as Walter. So having a beautiful earring, her name is Erin. So we are making strong connections to it. So, but the connection, more than a strong connection, the connection has to be robust so that when a new person comes, we will be able to recognize them better. So because here, when the new person comes with a big mustache, we have no way of saying that person is a new person. So here our training is good. So in a positive way, we can say that it has high accuracy or low training error. But what happen? Our training is good. We have low training error. We have high accurate result. But what didn't happen is that our generalization error is low. Sorry, our generalization error is high. Our generalization accuracy is low. So both in the previous examples in the last class, if you remember, we spoke about a dog example. If a dog has a pons in its tail, it is called as poodle. So whichever dog has a bob at its end, we call them as poodle. So here also, whoever has a big mustache, we name them as Walter. So with people and dogs, what has happened here is that we have learned overly, like we have overlearned it or we have overfit into the input data. So we have learned too much, we have paid too much attention to the one particular feature called mustache. So we have paid too much attention. So that has misled in the generalization. Machine learning systems are really good in overfitting. So there are two actions to control the overfitting. What is that? The first one is regularization. So regularization means to keep the rules as general as possible and as long as possible, so that we can avoid slipping into the memorization process. The second step is stopping the training. Whenever we are about to flip into the memorization process, we should stop the training then and there. So these are the two techniques which can be used to avoid overfitting. Is overfitting clear to you? Overfitting means it has learned the rules very well. But what happens is that the training is very good, it has learned the rules very well. But what happens when the new data comes, they perform poorly. So we saw an example where a person having a mustache is named as Walter. So even when in the future, when some person with a big mustache comes, we immediately try to associate our mental picture with Walter, and we name them as Walter. Whether the new person is Walter or not is a different story. But immediately when we see the feature of mustache, we recognize them, recognize that person to be as Walter. So that is here what we have done is that we have overlearned about that feature. We have overfit the input data. So what happens here is that the training is good, but the generalization is bad. Generalization or validation is bad. So we have high accuracy in training, low training error, but the generalization error is high and the generalization accuracy is low. So this is what has happened during the overfitting. So overfitting can be avoided by two-step process. The first step is called as generalization. So in generalization, what we do is that we encourage the system to keep the learning rules as long as possible so that we can prevent it from memorizing the detail. So the second step is that we need to stop the training. Immediately it is flipping into the memorization. We will stop the training then and there so that overfitting can be avoided. Is it clear? Okay, now we will understand what is meant by underfitting. The opposite of overfitting is underfitting. Overfitting means learning the rules too precisely. Underfitting means learning the rules to be too vague or learning very generic rules. This is called as underfitting. So this is usually much less of a problem when compared with overfitting. How can we avoid this is by adding, we can avoid underfitting by adding more examples. By adding more training data, we are allowing the system to learn better rules for understanding from that piece of data. Because it is learning generic rules or the rules are very vague. It does not have enough information to learn more rules. So what we have to do when we are underfitting, we have to supply more examples to the system so it can learn the rules better. So that in that way we can overcome underfitting. How we will overcome overfitting? By regularization and stopping the training earlier. But here, how we will overcome underfitting? By adding more training examples. So let us explain this with a graphical plot. What is epoch? We saw in the last class. Anyone would like to recollect what is epochs? So if you look at this graph, this is a graph between the error and the epoch. So what happens in this quadrant is that this solid line is indicating the validation error and this dashed line is indicating the training error. So when we start the training, epoch is nothing but how many times. So it is one epoch is one time of completely seeing the all the training data is called as one epoch. So number of epochs is the system has seen the entire training data set that many number of times. So when we start the training during the initial epochs, what happens? Both the training error and the validation error was high when we are starting the training, and it is in the underfitting mode. Initially, when we start, we would have not seen many examples. We would have seen very less examples. Then what would happen when we have seen less examples? It would have learned the rules very generically, and the rules are vague. So both the training error and the validation error or generalization error is high at the start of the training. But as we when we progress with our training, what happens? Both the validation error and the training error is coming down. At one point, what will happen is that our training error will continuously continuously will reduce because it is still learning from the example, so that it is continuously decreasing. But after one time, what will happen is that our validation error will flatten and then it will start to increase again. So this point, when it starts to increase again, when the validation error is increasing again, when the training error is getting low, is called as overfitting. This area, this region, when the moment it starts to increase again, is called that moment. From that moment, the system is entering into the overfitting mode. So what we are doing is that we are learning from the samples in the training data set, and we are periodically checking our performance using the samples in the validation set. So so we are reporting both the errors. We are reporting both the training error and the validation error. So initially, when the training is started, the it is in the underfitting mode because it has not seen enough examples. So both the training error and the test validation error is high, and it is continuously starting to decrease as it sees more examples. At one point, what happens? The training error is continuously decreasing, but the validation error starts to increase. That is the area where we are entering into the overfitting. Is it clear? So this will happen in any case. Whenever our validation error is after decreasing, if it starts increasing and our training error is getting low, that is when we will understand our model has gone into overfitting. This is a common process which we need to understand. Let's take one example. If you look at this example, we want to separate. It has both circular data points and square data points. So if you look at here, in this one, we have a boundary separating the circular data points and the squared data points. In this, among the square data points, there is a circle here. So what the boundary has done is that it has made a very specific curve. So it has, so we can say this is a likely case of overfitting. So it has separated very accurately. It has gone inside the squared region and then circled the circular point. This is probably a better curve. Though there is a false positive here, what we have done is that we have tried to eliminate it and we have made an optimal fit here. The input data with the boundary curve that separates the two different set of points are shown here. So what happens here, we have only one circular point that is deep into the square territory. We can call this point as an isolated point or an outlier. It is natural to treat it with suspicion. Suppose we do not know if this is a pattern in the data distribution or it is just an outlier, we never know. If you have more data like this, then we can come to a conclusion whether it is a pattern or not. If we don't have more data, we have to come to a conclusion with what we have. So here we assume that future, if some data is going to come, that is likely to be square than a circle. So we can consider this point to be as an anomaly. Since the circular point is isolated and no similar points are existing nearby, we can infer that the future points in this region also will be a square category. However, with more data, we can get into better conclusions. So this is how overfitting looks like, and this is how the normal trend would be. So earlier we said there are two ways of controlling the overfitting. One is by regularization, another is by stopping the training. So now we will see how we will stop the training. So here in this curve, what we learned is that after a certain point, what after this certain point, what happens is that the validation error flattens and then it tries to increase again while the training data is decreasing. So what we can understand from here is that why the training data is decreasing is that because it is continuously learning from the input data, it is digging deep into the data, and so it is learning more about it. So the training error is coming down. But what happens to the validation error? It has So the validation error initially it drops. So after some point, what will happen is that when we are training with more examples, the error is going higher. So is it clear? So what we will do is that at the moment the validation error is going high, at this point we will understand that validation error is going high. At that point, we will stop the training. We are not stopping the training very early, or we are not stopping the training at very late after learning many things. We are stopping at the right moment when the validation error is going high. This concept is called as early stopping. This is a much sensible stopping because we are not stopping at the beginning, or we are not stopping too late. We are stopping right at the moment where the validation error is going high. So the training is fair at this point of time. Before it enters into the realm of overfitting, we are stopping the training, and this concept is called as early stopping. Most of the times when you look at our error curves, it will be like this. So there is no proper way of saying like that there will not be a smooth curve like this, whereas we will have a very noisy curve. So we will not be able to correctly pinpoint where our validation error is getting low, or where our validation error is increasing. We will not know whether it is a momentary increase or it is a regular increase. So what we do is that there are a lot of algorithms to smooth out these curves. So we use that algorithms to smooth these curves, and then we find the increase in the validation error and we stop there. So this is called as early stopping. Any doubts here? So what we did in underfitting is that learning the rules very vaguely, or learning only the generic rules. To avoid underfitting, we need to add in more data. When we will have underfitting, when we are starting the training, our model will be in underfitting mode because we don't have enough examples to learn from. So the rules will be very generic when we start up the training. But when we proceed with the training, what will happen is the training error will continuously decrease and the validation error will start to spike again. So when it is spiking again, we are getting into the realm of overfitting. So to avoid overfitting, there is one concept called as early stopping. That is, we have to overfitting mode. So thereby we can avoid being in the overfitting region, and we would have learned enough training samples by then. So this is a concept of early stopping, and there are a lot of libraries available to implement this one. So next we will see about regularization. So what is regularization? So regularization, we saw that it will avoid slipping into the memorization process. So when we have the training data, we often squeeze a lot of information out of it to learn or to extract meaning from the data. Early stopping is one way to manage that overfitting, but there are other techniques that can help reduce the tendency to overfit. Because early stopping, we are not giving the permission to the system to learn more data. So what will happen is that we want to train longer, or otherwise we want to push both training error and validation error to be low. So either if you want to train longer or you want to make both the errors low, then what we need to do is that we have to do regularization. Early stopping is just making the training stop at one particular point. But whereas here, this is a different technique where it can allow longer training, and at the same time, it can reduce the error. This is called as regularization methods or regularization. We will see how to do that, because computer does not know the line between what is a good knowledge from the input data or overly specific knowledge from this particular point of data. It doesn't know the difference between those two. So what happens? It doesn't know it is getting into overfitting. It will continuously learn. So there should be some external factor telling us that you're overlearning it. So if an external factor is not there, it will continuously learn. It will not know that it is overlearning. So there must be something that is controlling the overlearning. In addition to the learning algorithm, there must be something to tell that the system is overlearning. So the popular type of information to include this is to limit the size of parameters. Limit the size of parameters used by the classifier. So what we will do is that we will keep the parameter sizes small so that this can prevent from one feature from dominating from others. In our previous example, we saw that if a person has a big mustache, immediately it is making a mental picture as Walter. So what we can do here is that here we are not paying attention to other features like height, shirt color, voice, personality, or skin tone. We are not considering all other features. The only feature which is dominating is mustache. So when what will happen when we limit the size of parameters, we will pay equivalent attention to all the features, and we will not allow one feature to dominate. So it is not like we are setting equal importance. We are setting equivalent importance to all the features so that one feature will not dominate the all other features. Thereby, overfitting will not. When we pay attention to all the features, what will happen? One feature is not getting dominated. So we will have a robust connection between the features and the names. So there is a different set of connections which is made. There is no one feature which is dominant here. So we are trying to make sure that no one spams the others. So this will weigh down to the small values. It will prevent overfitting. It will help us learn more information from our training data. The amount of regularization is given by lambda. So if lambda value is very high, which means more regularization. If lambda value is low, it means the regularization is poor. So with high values, you can have smooth boundaries. With low values, it can precisely adapt to the data. So if you look at here, it has a high value of uh, regularization. So the boundary is very smooth. Whereas here it is precisely adapting to the data. So the regularization parameter value is very low here. So the larger values of regularization will smooth out those curves out. Apart from this one, there are two additional specialized regularization techniques. One is called as dropout. What is dropout means? We temporarily disconnect some of the elements from the network so that we can force the other elements in the network to participate. The second type of regularization technique is called as batch norm or batch normalization. What is batch norm is that we will adjust the outputs of each layer so that no element will dominate the other element. So it is nothing but adjusting the outputs of each layer. So no element dominates. Is it clear? So far what we have seen is that we have seen the concepts of underfitting and overfitting. When we will have overfitting is that when it has learned too much. Underfitting is that when he has learned less amount of data. Sorry, when it has learned generic rules, we call it as underfitting. We saw some examples for both underfitting and overfitting, and we also saw the techniques for controlling the overfitting because it is the biggest problem. How we will control underfitting is that we will give more examples to learn, more training data to learn so that underfitting can be controlled. Overfitting, how to control it is by two techniques. One is regularization, another one is early stopping. So using these two techniques, we can control that one. And apart from that one, there are two other techniques which is called as dropout. Dropout is temporarily disconnecting some elements and which will force the other elements to participate. And batch norm is adjusting the outputs of the output layer so that no element dominates. So is it clear? Next, we will talk about bias and variance. So these ideas are also related to underfitting and overfitting. So what does a bias means? Bias is a measure of tendency of the system to consistently learn wrong things. What is variance? Variance is a measure of tendency to learn irrelevant things. It's a tendency to learn. So today we will explain both the concepts using the graphical approach. So it is not that this idea of bias and variance are limited to only one type of algorithm or 2D data. But for the purpose of explanation, we will use 2D curves to discuss this one. We will focus on how to find a good fit with the underlying noisy curve. So let's imagine there is an atmospheric researcher. She is measuring the wind data on the top of the mountain. So every day for the whole year, at the same time, she is measuring the wind data and she is plotting the wind data. So this is wind speed versus time. So she is plotting the wind speed against the time. So she gets a very noisy data. So this is measured for the whole year, every day at the same time. So if you look at this data, the data has an underlying curve to it. So it has an underlying curve. Though it is noisy, it has a underlying curve which fits it very well. So we can call this noisy curve to be as an idealized curve plus noise. So we have an idealized curve like this, plus we have some noise factor. So these two together forms this curve. So what happens is that she has a good model for describing the noise, whether that noise can be uniform or Gaussian, but her description is only statistical. Her description is only statistical, meaning that she does not know the exact values of the noise so that it can be subtracted from it. So what she does is that she takes the curve, underlying curve, and fits a underlying curve to it. So this is the original curve, and this one is the curve which is fit to it. Fit to the noisy algorithm using fit to the noisy curve using some algorithms. So what we can do is that we can use the idea of bootstrapping. We can take 50 versions, we can make 50 versions of this curve. Each version takes 30 points. So what we are trying to do now is that we know that we have a curve and uh, we have fit the underlying curve using a curve fitting algorithm. We have fit the curve. Then what we are doing is that we are trying to take samples from these curves. So each sample consists of 30 samples. So like this, we are creating 50 samples, 50 curves. So we have created 50 curves. Each curve has taken 30 points from the original curve. So if you look at it, if you look at these three graphs, I'm adding an additional curve to it. If you look at these curves are not tracing through all the points. It is tracing through only few points. This green curve is tracing only through few points, but it is not following all the points. So I can tell these curves has high bias. But when you add all those curves together, when you put in all the curves together, all these curves are looking very similar. So you can say they have low variance. Though they are not passing through all points, they look very similar. So they have low variance. So now let us imagine that We have other curves. We are fitting another curve like this. So these pink curves are flowing through most of the points, and it has lot of hills and valleys. So we can say that they have low bias because it is passing through most of the points. If we put together all the curves together, there is a lot of variations to it. They are not similar to each other. So we can say it has high variance. Is it clear? So when the curves are not similar to each other, when they have a lot of hills and valleys, we call them as, because these curves are quite different from one another. Otherwise, we can say they have high variance. Previously, they vary from one another, but they look similar to each other. They are pretty much the same. So we call it as low variance. When we call them as low bias, we call them as low bias because they are complex and flexible to accommodate most of the data points which are flowing through it. So we call it as low bias. But on the other hand, when the curves are simple, smooth, and it was gentle upward curve, the curves are looking similar to each other, but they are not passing through most of the points. They are passing through only very few points. So we call them as high bias. So is low bias, high bias clear? Okay. So we have seen overfitting and underfitting, and we saw an example of bias and variance using 2D curves. If this is clear, we will go to the next topic. This overfitting is a major problem in machine learning. So whenever you train your data, so you need to be careful looking at when the validation is going, when the validation error is going high, and you have to make sure you stop it before it, or else you use some regularization techniques like batch norm dropout to overcome that one. So that one you have to take care of. So now we will go on to the next topic, neurons. So now I would like to invite somebody to invite you to tell what is called as neurons. So anyone would like to tell what is neurons? You know much better than me. Should I call somebody? Varshini, would you like to tell about it?
Neurons are a part of central nervous system.
You're not able to hear me. Am I audible?
Yes,
Someone?
ma'am. I'm able to hear you, ma'am.
Okay. So neurons are a part of central nervous system. Then?
Yeah. Ma'am, they act as a basic unit of transmitting information.
Okay. Then? Any
Ma'am,
other
they
point?
don't have regenerative property.
Okay. Next. How
One
they
neuron
communicate?
receives one
Yeah,
neuron receives information from multiple neurons.
very good.
Ma'am, they have both a convergence as well as divergence property depending on the location of the nerve of the neuron.
Fantastic. Then?
They transmit information through electrical impulses.
Fantastic. then because today we are going to see how an artificial neuron is inspired from the real neuron. So we need to brush up our knowledge on about real neurons. So would anyone like to discuss about the structure of the neuron? Because they form the basic part of our cognitive ability. So anyone would like to tell what is the structure of the neuron? So we have our artificial neurons inspired from that one. So we will be learning it. So would anyone like to discuss this? I can draw the structure, someone can
Yes.
explain.
It has a cell body and a long tail.
Yeah,
which
it has a
transmits
cell
on-
And
body.
they have dendrites,
Yeah, it
Dendrites,
has
nucleus,
nucleus,
axon.
axon, myelin sheath.
it has axon.
And the Schwann cells in between.
So I'm drawing another neuron here. So what is the connection between them?
synapse.
Synaptic
Synaptic.
terminal.
Yeah. So this is correct, right? So it has a cell body, it has a nucleus, it connects with other thing with dendrites. The connection, the strong connection between the two is called as axons, and it has synaptic terminals. So this is a sketch of the brief sketch of the biological neuron. So we know it is a complex and a sophisticated process because it involves chemistry, electricity, timing, proximity, and so on. So can somebody talk about neurotransmitters? We are missing out on it.
Ma'am, they are chemicals which are released in the synaptic terminal, which goes and activates the electrical impulse in the adjacent neuron, ma'am.
Fantastic. So information comes in the form of chemicals, right?
Yes, ma'am.
Yeah.
Yes,
So
ma'am.
can somebody say how it receives the chemicals, how it translates into electrical charges, action potentials, and can somebody discuss that one?
Ma'am, for example, acetylcholine present in the synaptic vesicles is released when the impulse is passed because of calcium action. When this acetylcholine combines with the adjacent neuron's uh, acetylcholine receptor, the sodium channels open up there, ma'am, and the impulse passes to the neuron for the information transfer.
Yeah. So I will talk about things which is really needed for this. I'm not an expert in neurons, but I will just tell what has inspired the artificial neuron. So we know that we are receiving chemicals, information comes in the form of neurotransmitters. So a neuron receives it and it receives information from all other neurons and it converts into one, so it adds up. If it is above a threshold, it converts into one electrical charge. That electrical charge is transmitted to another neuron and it will make the other neuron to release another set of chemicals. So this is how information is processed for all the information transfer for all our mental abilities. So this is how the information is getting processed. I will not say that all the machine learning algorithms depend on artificial neural networks. Sorry, artificial neurons. Only few techniques depend on it. Most of the techniques have direct mechanism and they use explicit equations to arrive at the solutions. No neurons is needed. But if you look at neural networks, deep learning, so such algorithms need artificial neurons. So today we will see how to design, build, and develop the deep learning systems. So this is the foundation for the deep learning systems. So, and there is one more technique which we need to learn. Sorry, one more terminology. The map of the individual neuron connections is called as connectome. So we all know this connectome is unique as a fingerprint and iris. So here also, we will not say as connectome, we will see the different connections in the artificial neurons. So many people have tried to mimic the model of brain, model of this neural connections, but they are not successful yet. But many people have built the mathematical model for it. So artificial neurons is one. It is inspired by the real neurons. It has the resemblance, but only in the general sense. Here also we have the connections, but it is only in the general sense. It is not completely mimicking it. It is a simplified form of the real neurons. Artificial neurons are just a simplified form of the real neurons. Most people still prefer to call them as neurons, or else we can call it as units. So the history of artificial neurons started in 1943. So the contribution of the work is any logical expression can be, with satisfying certain conditions, can be neurons. So what we are saying is that the neuron can perform a mathematical logic or a mathematical function. So artificial neurons provide a bridge between math, logic, biology of neurons, and the brain. So it acts as a bridge between these concepts. So what is an artificial neuron? It will take any logical expression and implement it. So the logical expression can be mathematical operation also. Any logical operation satisfying certain conditions can be implemented using an artificial neuron. So usually, if you call a function as f of x, you have x as your input and you have a function f and it will give you an output y. This function can be anything. This input can be anything and the output can be anything. So this mathematical function can be expressed in the form of neural networks. So this function can be any mathematical operation which can be applied on the input and we will get an output. So neural networks is it's a function estimator. So it will implement any function which you give it to it. So any of your problems which has a certain conditions can be implemented it. So we will not say it will solve only this problem or that problem. It can solve any problem providing it has some certain conditions to implement and it has certain functions to implement. It can be implemented using neural network. So in 1957, perceptron was introduced for the first time. It's a simplified mathematical model of neuron. It's a simplified mathematical model of a real neuron. So what it has is that it has number of inputs. So this is called as a perceptron. So what here we have is that we have the inputs. These inputs are real numbers. And we have each input has one weight. So this weight is also a real number. So what we will do is that we will multiply the input number with the weight. And then similarly, we will multiply all the inputs. We can have up to n inputs. So all the n inputs are multiplied with their corresponding weight. and they are summed up together. If the summation is greater than a threshold, here I have fixed the threshold to be as 0. If the summation is greater than 0 from all the inputs, if the summation is greater than 0, then the output is 1. If the summation is less than 0, the output will be -1. So this is the model of the perceptron. Simple model of the perceptron. So it has an input, which is a real number. It also has, every input has a weight. So the input gets multiplied or scaled by the weight, and they are summed together, and they have a threshold value. So it is, the summed value is compared with the threshold. If it is greater than the threshold, we have one value. If it is lesser than the threshold, we have another value. This can be even 1 or 0 or 1 or -1. So this is the simplest model. So the basic mechanism has persisted. So this is similar to a neuron. So what you have there, you have the neurotransmitters coming. All the transmitters are summed up, and the summed up one is compared with the internal thing. So if it is greater than the threshold value, it produces an electric charge, and the electric charge will go and induce the other one, and it will produce the chemical. So similarly, it is inspired from it. So here we have numbers. We don't have chemicals or electrical charges. So here both the input and output is a number. So the modern artificial, this is a model of perceptron, which is a simplified model of the neuron. So we have the modern artificial neuron. The model artificial neuron has two changes, one at the input and other at the output. So in the input, what is the change is that we have another term called bias. So this bias is not coming from any other neuron, added to the summation. Whereas this input 1, input 2, input 3, all these are coming from the output of other neurons. Whereas this bias is not coming from any neuron. It is just added to that. So maybe I will draw it separately. So perceptron doesn't have a bias. So the model artificial neuron has the same model of the perceptron, but it has two changes. The first change is at the input, where we have an additional input to the summation, which is called as the bias. And the second change is in the output, where we have a activation function. Here we had a threshold, but here we have an activation function. So this activation function is a mathematical function. So the summation is compared with the activation function. So the summation is given to it. So based on the function, it will produce an output. So there we use the threshold. Here we use a activation function. Here I have mentioned as a step function. So these are the two changes which are made to the perceptron to make the modern artificial neurons. So, and also what we will do here is that we will not explicitly mention the multiplication with weight. So if I write input here, it is implied that the inputs are multiplied with its own weight and then it is given. So unlike here, I'm not showing the weights here. So if I write weight 1, it means that this input is scaled by weight 1. This input is scaled by weight 2. This input is scaled by weight 3. I'm not explicitly mentioning it. And the bias also has its own weight to be multiplied. So what I will do here is that I'm not explicitly showing the multiplication with the weights. And the other thing is that instead of adding this bias separately, so if I write input like this, it means that it is getting multiplied with its weight and then it is going to the summation. So what I will do is that I will take bias as one more input. Initially, I am adding it separately. Now I am taking by considering bias as the fourth input, called as a bias trick, because it is easy to compute. So if I consider this as one more input, so and I'm considering it as an input, so this is called as a bias trick. So instead of writing bias, I can mention it as input 4. Sometimes even if I don't mention bias, it means that every neuron is added with its own bias. So similar to the real neurons, the entire thing I can represent it in a box. So So the output of this neuron can be connected to this one. Output of this neuron can go from here. These dotted lines shows that the output is coming from elsewhere. So like this, we can have the interconnection of all the neurons. Output of one neuron goes as an input to the other neuron. So later on, we will not be representing like this. We will just represent one circle. One circle means one neuron. So for example, imagine that you have 6 neurons. Let me name it as A, B, C, D, E, F. So these 6 neurons, the output of this neuron is going to all the other 3 neurons. So this one is going to all the 3 neurons. The output of C is going to D, E, and F. So how can I, there is one way of convention. One convention is that we can write the weights as like this, AD. AD means the output of A is given to the input of D. So the weight of this line is given as AD. So this one can be written as AE, this can be written as AF. So similarly, this one is written as BD, BE, BF. This one is CD, CE, EF. So to sum up this one, so what we have learned so far is that we learned that we know that the real neurons are complicated electrochemical nerve cells. They accept chemicals as input and they turn into electrical charges and all the electrical charges. If the charge is above the, excuse me, just hold on for a minute. So if the charge is above a threshold, the neurons release new chemicals that travel to other neurons. In this way, that every neuron will receive a new image and many other neurons will also receive and transmit to the other neurons like this. So we have inspired, so researchers have inspired the basic function of neurons and they wanted to represent logical statements using artificial neurons. So today's artificial neurons are nothing but bunch of numbers, input numbers, and they also have another number called as bias. So every input is scaled by its corresponding weight and they are added together. The resulting thing is nothing but a little mathematical function. So the summation is given to the activation function. Activation function is nothing but a mathematical function. So which computes a new number based on the neuron input. So it has a neuron output. That output will usually serve as a input to other neurons. So taken to all these. So if you look at this one, all these interconnected neurons are called as neural networks. Neural networks are nothing but the interconnection of several neurons. How they are connected, in what way they are connected. So in deep learning or in artificial neural network, we will be seeing how each neurons are connected together. The basic function of neuron is just this. So or else I can say this one. So you have the inputs coming from the output of other neuron. They have a weight, which so that every input is scaled by the weight, and it also has another input called as a bias, and also after the summation of all the inputs, it goes through the activation function where it performs a mathematical function and produces the output, and this output is connected to the other neurons. So hereafter in the next class, we will not be drawing the detailed version. So if I want to represent a neuron, I'll be representing like this, and the connections will be represented like this. Is it clear? Any doubts? Okay, if you don't have any questions, we will meet in the next class. Next class will be on Friday. Thank you all.
Thank you, ma'am.
Thank you, ma'am.